A few special type of sequences that you have. One of them is a geometric sequence. A geometric sequence is of the form a times a times r square, a times r cube, and so on and so forth. That means you start with some number a and you obtain the next number by multiplying the current number by r. So initial term is a, and there is a common ratio of r between any two terms. So essentially you multiply by r to the current number to find the next number in the sequence. A geometric sequence is a discrete analog of the exponential function. So if you think about this exponential function, f of x is equal to a times a to r to the power x. This is an exponential function. What we are doing is we are finding discrete values of it when x is 0, 1, 2, 3, and so on. The sequence Bn, which is minus 1 to the power n, this is a sequence that starts with 1, then becomes minus 1, then 1, then minus 1, and so on and so forth. This is a geometric sequence. The first number is 1, and you multiply by minus 1 every time to find the next number in the sequence. If I look at the sequence Cn, which is 2 to the power n, then this sequence for n is equal to 0, it's 2 to the power 0, that is 1, 2 to the power 1 is 2, 4, 8, 16, and so on. One thing that I'm going to ask you to do is remember to the power n for n is equal to 0 to 10. This is something that I want you to calculate, and I want you to remember this to the extent that if somebody wakes you up at 3 o'clock in the night and asks you what is 2 to the power 7, you should be able to answer it. This is something that will come in handy for lots and lots of courses subsequently. So if this is something that you are not familiar with, make sure you do this as soon as possible and keep practicing it so that you don't forget. Let's come back to our sequences in summation. This is a geometric sequence. The first number in the sequence is 1, and you multiply by 2 every time to get the next number. This is another sequence we just made up. It is 2 times 1/3 to the power n. So in that case, the first number will be 2, then 2/3, 2/9, and so on and so forth. This is a sequence where a is 2 and r is 1/3. Note that r doesn't have to be an integer. R can be any number we like. An arithmetic progression is a sequence where the way we identify the next term is not by multiplying the previous term, but rather by adding something to the previous term. So it is of the form, the first number is a, the second number is a plus d, the next number is a plus d plus d, then the next is a plus d plus d plus d, and so on and so forth. A can be any number, d can be any number, and it will give you a different sequence every time. So arithmetic progression is a discrete analog of a line. So the line function we can think of is that as y is equal to d times x plus a. This is a discrete version of that linear function. This is an example of an arithmetic sequence where the nth term in the sequence is minus 1 plus 4n. So we start with minus 1, then 3, then 7, 7, 11, and so on. So here the first term is minus 1, and you add 4 every time to get the next number. If I look at the sequence 7 minus 3n, then I will have a sequence that starts with 7, and the difference is going to be minus 3. That means every time I want to get the next number, I have to subtract 3 from the current number. Strings are a sequence of the form a1 through an. So in a sequence we had different terms. In a string we are going to concatenate them together. The length of the string is the number of terms in that string. So if I had the empty string, that means it has no terms, its length is 0. There are some special integer sequences, and our goal is to look at if there is a way we can figure out a rule or a formula for that sequence so that we can find the subsequent terms. So if you are given a sequence, then in order to find what the corresponding formula for that sequence is, there is no sort of fixed set of rules, but this is sort of a guideline that works. First ask, are there any runs of the same value? Are there some terms that are obtained by previous terms by adding something, by multiplying something, etc.? Are terms obtained from previous sequence? If I look at the ratio of those, then is the ratio constant? That would suggest that it is a geometric series. And we could be using both of these versions. That is, we could have a sequence that combines some aspect of arithmetic sequence and some aspects of geometric sequence, and we'll see some examples like that a little later. So let's look at the sequence 5, 11, 17, 23. What does this sequence represent? You can pause the presentation here if you need more time. Otherwise, I'll be going to the answer right now. So what I can observe here is the difference here is 6, the difference here is 6, and so on. It suggests that this is some kind of an arithmetic sequence. So now that the difference between two numbers is 6, that means I'm adding 6 every time. That means the sequence is going to be something plus 6n. So that every time I increase the value of n by 1, the value of the term will increase by 6. And now we can figure out that, well, the first term needs to be 5, and that will tell us what this number is going to be, and that is going to be 5. Here we have another sequence. It's a little bit more complicated. Identify what this pattern in the sequence is. Again, you can pause the presentation till you are ready. Okay, so this sequence appears a little bit more complicated, but what we can observe is if I add 2 to every term, then I will get 3, 9, 27, 81, and so on. So essentially, if I add 2 to the sequence, then it will become like an arithmetic sequence. But the first term needs to be 1 rather than 3, and that means we have to change the formula a little bit. And the answer in this case would be 3 to the power n minus 2, where n is from 1, 2, 3 all the way up to infinity. Let's look at this sequence. So this sequence is not something special. It just want to show that the formula can be kind of strange. In this case, the formula happens to be square root of 2n plus half floor of that, which is also can be written in this fashion, which is 1 plus square root of 1 plus 8n uh, divided by 2. Here are some important sequences that you should be aware of. Some of the sequence that is the first few squares, first few cubes, to the power 4 not as important, 2 to the power n, this is absolutely must that you remember. N factorial, a few of them are useful, at least this part you should remember. Once again, we have reached the check before you go ahead slide. This module should be fairly straightforward in terms of things you should have already been familiar with, especially with arithmetic and geometric sequence. If you have not seen that recently, you might want to look into what it is and that you understand how those sequences behave. Here is a simple problem to work on. Find terms in this sequence for values of a1, a2, a3. Again, the answers are at the bottom. We have reached the end of the module, so please go ahead, do the review quiz.